All right, hello everyone. Welcome to my talk. I'm here today to bring you grafting apple trees, not in a literal sense, because that'd be very unfitting to this talk. But I think as we go on, you'll see why I chose this name. So my name's Jaron Bradley. I work for Jamf Protect, doing detections, research, and development. The last two times I've spoken here, I worked for CrowdStrike. Decided I wanted to take a jump and move to a small little startup life again. I miss startup life, so I jumped and joined Digita Security with Patrick Wardle. And then a month later, we were bought by the large Jamf company that we are now. So startup life didn't last long, but they're treating us really nice and we're having a good time over there. So today, I want to talk to you about incident response and the process tree. So the reason I bring this talk up and why I think it's so relevant is because in traditional incident response, you want to get a list of processes. If you've been to any of my talks in the past, you know that I'm very reliant on the process tree to do the work that I do for detections development, for incident response, for threat hunting. Like, it's very, very relevant to know what processes are running and what led to the execution of those processes. So on macOS, if you do a process listing and you get a list of all the processes that are running, what you'll see is that, at any given time when I run it, somewhere around 90% of processes run as children of launchd. This is just due to the unique XPC nature that is Apple. And from a threat hunting perspective, it is not helpful whatsoever. But there are ways to dig into this and gain more detail from currently active processes. And that's what I'm going to be sharing a good bit of today. Apple also removed the pstree command, probably for this reason, for the fact that the data it was returning is not really that helpful. But the pstree command was removed sometime around Mavericks, and what I want to do is rebuild that pstree command and make it far more useful than it was, so that it actually serves a purpose. So this is kind of a good example of what a process tree looks like on Mac and what a lot of different software and process monitors and endpoint solutions, a lot of what they'll show you is something like this. So let's say that I open finder.app and I go to the applications directory and I double click on Google Chrome. And then I go to Spotlight with Command Space and open calculator.app from there. And then I go to the dock at the bottom, the left, the right of the screen, whatever, and I open calendar.app from there. And then finally, I go to the Chrome instance I already had open. I go to the URL, and I open a terminal by using the custom URL scheme that allows me to open a terminal with a man page. Yes, this is a thing. I'll get into it later. But this is what we see. This is what we see after I've done all those things. And that's, we see Google Chrome, calculator, calendar, terminal.app have all spawned from the same process. Launchd is their parent, even though we open them all through different apps that are running on the operating system. The only extra thing we see is like a Google Chrome helper running under Google Chrome. That'll happen. That's pretty standard. So sometimes we get further hierarchy, but most of the time it's pretty linear in that we just see apps running under launchd. A more useful tree, at least from an incident response perspective, would be something that tells us more information like this. The fact that, hey, calculator.app was open from Spotlight, calendar.app was open from the dock, Google Chrome was open from Finder, and then Terminal was launched from Google Chrome. Now this, according to the standard pids and ppids, is not technically true, but this would be more helpful for us to know as a threat hunter rather than that bland, ugly process tree that we saw on the last slide. So the good news is all this information we need to build a more useful process tree like this is already available in the procinfo output. This is info that's held onto by launchd, and you can use launch control procinfo followed by the PID to get all this additional information that I'll be talking about today. Now, I don't use the standard launch control bash call for the tool I wrote, but it's totally possible. So if you're getting on a system and you want all the PID information possible, you want to run launch control procinfo on every single PID on the that is currently running. So that being said, these PIDs are not a secret. The tool I built is not through some secret, sauce. Really, these PIDs have been available for a long time by Apple. It's just nobody is really using them to their advantage. So the first up is the responsible PID. This actually is being used by Apple in their activity monitor. So if in Activity Monitor you open it up, and you see something like com.apple.audio.sandbox.helper, and you notice that in Activity Monitor, Slack is actually the parent of this process. However, if you look in the PS output, you'll see that according to PS, we take this same exact process that's running and we look at the parent and it says the parent is actually launchd. So Apple is doing some work under the hood to display this information to you already. So Sarah also touched on this briefly yesterday. If you were watching in her Apollo output, she had something called responsible path, and then she had path sitting next to that. So path is the process that's running, and then responsible path is the program that requested launchd open this program. So instead of looking at a parent of launchd for this sandbox helper, Apple has done the PID lookups to show you that although launchd is the parent, this sandbox helper process was created at the request of Slack. This is a hot topic on Stack Overflow. You can find a lot of different links and forums talking about, hey, why don't these really match up? Why are these so confusing? So you can kind of tear a bit of the responsible PID apart by looking at that. So if we look in the procinfo output, you see here in the BSD procinfo, I have a parent process ID of 1, which is launchd. And the responsible PID is 1377. This was a copy and paste from my terminal. Star is almost aligned for 1337 there, but it did not happen. There, right inside the procinfo, we can see the responsible path as well as the responsible PID. So these should match up. And we know now what was actually responsible for opening process 2939. However, inside Activity Monitor, the tool Apple supplies us to look at these relationships, they don't provide the parent process ID as an option to view inside the tool. This is probably because if they did show the parent process ID, it would be confusing because in the UI hierarchy, we would see one parent, and then in the output, it would be telling us it was a different parent. So I'm guessing this was removed intentionally for the sake of not confusing users. Which makes sense. The standard user is not going to care about these additional PIDs. They just want to see everything straightforward. So the next PID, I'm kind of coining this submitted by PID. It's not truly a PID field. In fact, if you're writing a tool to do this, you have to write something to parse this output, but it's a field called path, and this can be one of two things sitting inside this path. One of three things. The first thing it could be is non-existent. It might not even be there. But the second thing it could be is something that looks like this, where we have here, this is me looking at the procinfo output at a random time for my messages.app, right? Messenger, my iChat, whatever you want to call it. Inside of the procinfo for messages.app, I can see that this field, this path, says that messages.app was submitted by login window. So login window is a process on your system. When you shut down the computer, a bunch of plist information is saved for all the windows that were open and all the programs that were open. And login window is responsible at startup for going through each of those items and kicking them back off. So although the parent that we're told of messages.app is launchd, we can see inside the submitted by PID that login window, process ID 187 at the end there, is actually what was responsible for kicking off my messages.app. This is not a field that Apple is using. This is not being used inside Activity Monitor, and there's no way that I've found to really display this information in a useful process tree with tooling that Apple has already supplied. So submitted by PID is not really being used to display information to the user in any way. The other item that you might have inside the path field is a path to a plist, a launch agent or launch daemon. As you can imagine, this means at startup, if you look at the procinfo for a process and you see a launch agent in there, rather than a process starting this, its responsible item, or the item responsible for opening it, was a plist, launch daemon or launch agent. So instead of seeing launch D as a plist, we could manipulate a tree to tell us, hey, show us the plist instead. Now I find this really relevant from an incident response perspective because I hate running the launch control command, going to find a label that is actually of interest, taking that label and then digging through all the launch agents and launch daemons and trying to find and make this connection manually. It's just a pain in the butt, and quite frankly, it's a lot easier just to go find the running processes, look at the information, and see that a plist was truly responsible for spawning this. So once again, this is in the procinfo output, the launch control procinfo output, and if it's there, we're going to use it to our advantage. So there are times when the submitted by process gets terminated, and so we'll essentially what we'll have, this is a bit of a forensic item per se. So although the true submitted by parent of a process has terminated, that data is not going to be removed from the procinfo output. So we have information here about a true parent that's no longer running on the operating system. It's not going to show up in your PS output or inside your activity monitor or anything like that. However, the procinfo tells us that it was at one point running and it was responsible for the execution of this process. So here you see me taking the auto update submitted by item. This is for my iTerm2. So in other words, what happened was I got a little pop-up that said, hey, do you want to update iTerm2 to the latest version? I say yes. Auto update runs, it does the update, closes the terminal, and then it re-kicks it off. So when I go to look up the auto update process, it's no longer running because its job is already completed. So it's obviously not going to be there. So this is, regardless, even if it's terminated, we're still going to include it inside our process tree output because that's more evidence of what was running on the system. And we're here now, we might as well collect it. One other forensic item, and this comes down to a little more computer science-y, Unix 101, and that has to do with programs that have exec. This little forensic tidbit will only be in existence if the program is managed by launch D. So for the most part, this is probably not really going to fall into the realm of malicious software. This is probably just going to pick up additional processes for legitimate software that's exec. But what we have is this is what people in threat hunting tend to think everything should look like. And in a perfect world, it is what it would look like. Launch D, process 1, spawns process A, spawns process B, PID 1, 2, 3. However, and this is what a lot of endpoints show us, but it's not how everything works in the real world. There are a number of things that can lead to us getting really confusing process tree output. And that is when, well, there's a couple different ways this could happen. So when a fork occurs, a process clones itself. We get a new PID, that's great, it's awesome, but so here you see launch D spawns process A, that process forks, and we get another process A, but as a new PID. And that's fine, that's not a big deal. It almost in some ways works like a thread, but it's not a thread. Like there's a lot more going on there and more discussion there. But the other option when a process wants to create another process is it can call exec. So this is when process A would exec process B. However, what you're seeing here is not what you would see. This is what would end up happening. Process A's process image was just taken over by process B. The interpreter backdoor uses this. It's not really a technique. It's just it's literally a way of running programs on Unix-based systems, and it can lead to really confusing output. Because as you can see here, we have no evidence that process A was ever running. Instead, process A was running, and then something else just took it over, PID and all. So that being said, this is a fork exec, so process A forks, so process A creates a clone of itself and then it execs. So the next thing it does is that clone is taken over by a new process image. This is kind of what we really like to see in threat hunting because it's clear and it's obvious. That being said, all that information, what we can do is when we're running over every single process that's currently running, say we hit process B with no signs of process A, we'll check the procinfo, and there's actually two fields in here. One is program path, and the other is program. One of these fields is updated when the system execs. The other one continues to stay the same. So if we see a mismatch here, we can guess that what happened is the program probably execed. Again, this is only if the program is managed by launch D, but it's still good information to collect. So we can send a request to procinfo, we check, and now we can kind of rebuild this process tree on our own, kind of fabricating the information is here, but knowing that it's relatively accurate. So all that being said, if you don't care about any of that and you don't care about how it actually works, I'm introducing a new tool called TrueTree. So TrueTree is Swift-based. I have it open sourced on GitHub. It's lightweight. And it's good for IR engagement. So what this is for is it's for to get a running list of processes that are running on your operating system right now. It is not to watch in real time as these processes are created. It's to get in and out in a true IR fashion. So it does require root. Sending some of these XPC messages to launch D, as well as getting parent information, does require root for a number of these, unfortunately. So the first option is you can run TrueTree with standard switch, and that's going to give you just a process tree based on pids and ppids, just like PS tree would have done. Giving you, hey, and what I'm saying about that is it's the useless format, right? If you truly want it, or you truly need it, or maybe you need it for some comparisons and research, that's going to give you the version where launch D spawns about 90% of all processes. If you run it vanilla by itself, no arguments, then you'll get the actual, what I call the TrueTree output that uses the TrueTree concept. So this is going to go through all the items that we've just talked about and build a tree based on this information. So you see we getplists in there. We get to know what plists were responsible for running which processes. We get to know when a process execs, if it was managed by launchd, and we get to know when a process was terminated but launched another process. And again, this is just to add far more context to the process tree than we had before. And every process is sorted by the responsible PID and submitted by PID rather than just a parent PID and PID layout. Another switch that I'll talk about that I'll also include in some slides is the timestamp. So if you run it with a timestamp argument, you are able to see the times that each process was created. This will be relevant later in a different use case example. So again, I know some of this output might be kind of small, but I'll make sure you get your hands on the slides. This is coming back to the first scenario we talked about, opening apps in different ways. So here, these are all processes that would show as children of launchd, but in TrueTree we can see that LastPass, Activity Monitor, Keynote, Xcode, and Calendar were all opened from my doc. So wherever my doc's located, that's how I open these. And again, this information is relevant inside of incident response. I want to know if a user intentionally clicked an item or if it was spawned through some other way. And sometimes this is the only way to get that information. Same goes for Spotlight. So I can see Spotlight was created by spotlight.plist, and then under that, calculator executed. So yeah, the same goes for Spotlight, where I can see all children of the Spotlight process. And that's, again, doing the command spacebar and then typing in the program I want. And then Finder, the same applies. I can actually see children of Finder, programs that have been opened from the Finder app, rather than seeing these once again as launchd. If you double click a program or application in any way, it ends up showing as a child of launchd, unless you use TrueTree. I will say that a lot because it is very relevant, trust me. If you've had to put up with these headaches before, it can be a real pain. Login windows, so we already talked about this a little bit, but here I can see the programs that were open the last time the computer shut down, and those programs haven't been closed since because their true parent is the login window process. So I can see Spotify, Mail, and Slack were both all open the last time the system shut down, and clearly I have a lot of web content, children running under mail.app. We'll get into that in a little bit here. Here's an example of a process that is already terminated, and a good example of that is the open command. So the open command is used a lot in malware and also just in, it's a technique in general. So one use case that I can think of is if an attacker puts together some type of social engineering scheme to try and get you to open an application. You download that application, you run it, and it does something in the background. In the meantime, it runs the open command and it downloads a real document. That document is then used by Open to display to you, and this social engineering scheme looks a lot more convincing. Like I showed you a document that I was actually referring to in the email rather than nothing happening, which is really suspicious. So Open's kind of a great use case here. I can see that Safari, for some reason, and this was just an example, Safari was opened using the open command. Now, if anything's opened with open versus, another legitimate process, that's something you want to look into. This is indicative of a lot of different red team techniques, and again, a lot of social engineering type approaches to attacks. So I can see that Safari was open through open, and that inherently is somewhat suspicious, and I'm going to want to dig into that a little bit more. The same goes for AppleScript. So if a program is opened from AppleScript, also very suspicious, also very red teamy, hacky, and we want to know more about this. So this tells us that Safari was open from AppleScript, but AppleScript has since terminated. Otherwise, all we would see is that Safari was open from LaunchD, but instead we get this little extra tidbit of information. SSH. So SSH is actually pretty useful as it is. This is the standard output for SSH rather than the TrueTree model. And we can see I run the dash shell under SSH. I use this because nobody uses a dash shell, and it's a really easy way to Command F and find yourself inside the process tree. So this is actually the SSH output for standard. We can see it's pretty useful. Any commands run under SSH are gonna appear pretty accordingly. If we do look at the TrueTree output for SSH, we do get to see in there, as you probably saw in previous slides, that the SSH D keygen wrapper actually execs into SSHD. Just extra tidbits of information here. Again, we want all the context we can get, whether it's going to be super helpful or not. And this will work on more than obviously just SSH, but SSH keygen is a great example of trying to find an exec process that's no longer running. This is another SSH use case example. This is actually kind of interesting, a way to get context from processes alone. What you actually see happening here is me enabling SSH, or going into my system, going into my preferences, going into remote login, and then clicking on enable remote login. What happens then is smd.plist, which spawned smd, which I imagine is system manager daemon or something like that. I don't know, maybe somebody knows what that actually stands for, but either way, we know it's related to some of the system preferences and us changing those options, because when we enable SSH through system preferences, SMD ends up creating the SSH service rather than the SSHD.plist that we saw in the previous slide. So again, not really super relevant to an attack, but a cool way to see how we can get context into what happened just by looking at processes alone. Launch control. So a friend of mine last year brought this launch control use case to me, and maybe you're familiar with this one, but it still blows my mind. It hasn't been used in malware yet. I'm sure we'll see it somewhere in the future, but with launch control, you can create a launchd job using just the launch control command. So I can say launch control submit, then I provide a label that I want this job to have. So I just call it com.evil.whatever, and then I run calculator.app. So what this is going to do is this is going to open calculator.app. I can click on the X, it's going to close for about half a second, and then it's going to open again. I can click on that X as much as I want to, but as long as this daemon or this job is still enabled, it's going to keep recreating itself. So you can imagine if this was a background process or some type of malicious app, in some sense, this could be a lot more confusing. So by default in the standard tree, we see that calculator was created by LaunchD. No surprise. However, if we use TrueTree, we can see that we get this extra step where calculator was created by the launch control command. And this should almost never happen. There is some poorly written software that does this, and it drives me nuts. So you might run into this occasionally, but you should almost run into this never, where you find an application that was created by launch control. That's pretty inherently suspicious. So Office macros, this is what a Python backdoor looks like when it's running under a Office macro. This is the standard output. Now this isn't necessarily how it will look. There's a couple different ways to run commands from macros, and depending on how you use those will depend on what the parent actually ends up being. But the way I spawned this, a Python listener is now running, and it was created by Excel. However, we can't see that in the standard layout of pids and ppids. We see that launchd created Python, which tells us absolutely nothing. Python could have been run by anybody for anything, like if we're on a developer system. If we're not, maybe it's a little more suspicious, but just by looking at this process tree output, it tells me nothing. If we use the TrueTree method, we see instead, we get a much more verbose layout of the items that occurred here. And this might be relevant for a talk coming up later today, maybe not. But this is still an Office macro. And instead, in the TrueTree layout, we see that Core Services UI agent creates Microsoft Excel, which then creates this Python backdoor. So the Core Services UI agent, I kept seeing this as a number of different children for processes that would spawn. And after going to Scott Knight's blog, which was awesome, he has this brief documentation on some reverse engineering he did for Core Services UI agent. What I was able to piece together is essentially that Core Services UI agent is capable, in a very brief sum up, of taking user input and creating processes based on that input, usually through the UI in some sense. So what happens here is this is me going, I emailed myself a Python backdoor through with a macro, I opened it in mail.app, and then when you open that application, when you open mail.app and you open that email and you double click on the attachment, this is the process this is the tree that ends up getting generated. So the Core Services UI agent spawns Microsoft Excel, and that's because I'm clicking on icons inside of mail.app, and we end up with this process output. But again, this is far more useful than seeing that launchd created Python. This tells an actual story. If we truly wanted to try and get the process that or if we truly wanted to try and link this back to mail.app and know that this was a fish, we can take the timestamp of the Excel program. So the timestamp when Excel was opened, we can copy that. I usually go with the minute. It's kind of a good place to start. So I copy that, I do a Command F, and I do a search for other processes that were created at the same minute, and sometimes you'll get lucky. Some stuff does have to align for this to work, but in my case, it was pretty easy because I was just doing immediate testing. But what happened here is one of these web content windows, the web content processes, one of those was created for the current email that I had opened. So it was really easy to make this connection, but this isn't the only circumstance where timestamps will come in handy. A lot of times you can make these connections just by looking for processes that were running at the same time or created at the same time. And it all depends on what that process is doing and how long it needs to be opened. Another use case, I put Windtail here just because this isn't the Windtail malware, but this is kind of the same approach they took, and that was that the actors were using a custom URL scheme to get people to kind of, it opens up their malicious application in almost a more automated fashion. Still required a few steps for the user to click on, but it didn't require the user to go down to the app and double click it. Instead, they just had to click through some prompts. So here, I'm in Safari, and I put in xmanpage : who am I, and what this does is this tries to open a terminal. This tries to open a man page for the who am I command, and I'm brought a prompt from Safari whether I want to allow or deny this. So if I click allow, the man page is opened in terminal, and what we end up seeing, no surprise, terminal spawns under launchd. If we use TrueTree, we can see once again Core Services UI agent was responsible for this. So again, we don't get this direct connection to Safari like we would like to see, but we know that given it spawned from Core Services UI agent, there was some type of user interface, there was some type of user clicking here, whether that be through prompt or through icons or whatever. We know that there was some type of clicking here that was not a standard way of really opening a program. So we can deduce that this is something we want to look in further. However, with Chrome, since this is not an Apple process, Apple, a lot of times with the Apple applications, we end up with that Core Services UI agent. However, with Chrome, which again is not developed by Apple, instead we see terminal spawning directly under Chrome. Its parent is launchd, but its submitted by PID is set to that of Google Chrome. So this connection can be made really easily with other browsers. So this is kind of my grand finale, bring it all together to show why I think TrueTree is far more valuable than just standard PS output. Here, this is bringing both techniques together. This is an Office document delivered through a custom URL scheme. I am a bit surprised we haven't seen this in attacks yet, but you can deliver macro documents through custom URL schemes. So if I convince you to go to my website then redirects you to this link that you see up top. You will be asked if you want to allow the running of, or you want to allow the opening of Microsoft Excel. If you click Open Microsoft Excel, you're then greeted with the, would you like to enable macros? Assuming the user clicks yes, the macro is then executed and the backdoor runs. So here's what that looks like in TrueTree. Without TrueTree, each of these items would show as a child of launchd. So you'd have a Chrome instance, you'd have a Chrome instance, you'd have an Excel instance, and you'd have a Python instance. They'd all be children of launchd. However, with TrueTree, we get the nice layout that says, hey, each of these spawned one after the other, and they spawned each other. So we see that doc.plist requested the creation of the doc. The doc launched Google Chrome, and then Google Chrome launched Excel. Red flag kind of right there. Like what's happening, custom URL schemes are legit and they're there for a reason, but they're still pretty rare. And rare means we have a better chance of finding something interesting if we look at it. And then under Excel, we see Python, which by itself, we don't even really need the rest of this context, but it's really good to have to kind of piece the puzzle together. So if you need to reference any of that, right before I came up here, I kicked off my website, as promised, for those of you following on Twitter, which is themittenmac.com. TrueTree is available for download there. You can download it, play with it, go to the source on GitHub, whatever. The entire talk I've also posted in blog form under the blog section, both the idea behind it as well as the use cases that I explained there at the end. So please feel free to check that out if you're interested. And I think that's about it for me. Am I over time? Do I take questions? Should I just take questions back there? What's that? Okay. Any questions? I will also be back at the tools arsenal table after the next talk if anyone has any use cases in mind that they'd like to see in person. So feel free to come back and talk to me there as well. Yeah.
Have you seen any of the attacks you described in the file? Like these strange...
Macros. Macros are a given, and then the same applied to the mail.app and the open command, obviously used constantly in hacking malware, adware especially. Lots of adware using the open command, and that's why I think it's so relevant. Rather than to know launchd created something, at least we have that little tidbit, even if we can't keep climbing the tree, that open was involved in some sense. So yeah.
Do you keep a record about how many kick screw inception you've got, Python, OS6 scripts, Perl, whatever?
Yeah, so I don't really keep a whole lot of track of that. I do definitely try to come up with unique ways of opening processes and then see what that ends up looking like through TrueTree. That custom URL scheme one at the end with the Word document is probably the most, 3D inception processes I could really find. But for the most part, you end up seeing a lot of processes under login window. You end up seeing a lot of processes under Google Chrome that just creates a lot of children in general. And then there's a few others depending on how you use your Mac that might show like large process tree sections, I guess.
And then any limit of TrueTree, like,
Any limits? Like,
any limits,
I guess your screen size. Your resolution's too small. It's going to be it might look a little confusing, but otherwise that should be the only limit. It does its best to rebuild the tree based on all the PIDs and the information that exists. So. Cool. Well, feel free to come see me back there after the next talk. I'll be demoing it off. So.